Thank you. So without further introduction, I wanted to start the show and to bring up David Hill as our first presenter today. David comes to us from across the mountains as a civil engineering professor at OSU, and he's also a National Geographic explorer. David's been studying snowpack and water as a resource in the mountain environments for many, many years. So we're excited to have David here with us today. So thanks for joining us.
So just the right side. Excellent. Okay, fantastic. Good morning. I am so glad to be giving a talk in person. I teach at the university, and I have been lecturing to black boxes on the screen for far too long. So I'm really happy that you're all here. I'm really happy that there are also people joining the webinar online too. So I know it's tough to pull off kind of a hybrid thing. I'm really grateful to COAC for doing this. So anyway, great to see you all here. Okay, so before I get started, I want to just sort of make clear what it is that I'm here to talk about today, okay? So I'm not here to really talk at length about the coming season. There are better people to give that sort of talk. I'm mostly here to talk about seasonal snow, changes in seasonal snow, and those kinds of things. That said, the forecast is looking pretty good. Model ensembles consistently are predicting La Nina conditions right now through much of winter. So for context, the Climate Prediction Center at the National Weather Service, they issue watches if conditions are favorable for development of a La Nina, and then they will issue an advisory if conditions are observed and expected to continue. So that's kind of their two-stage process. And right now we are at the advisory level. There's not like a warning, like La Nina warning. So this is as good as it gets. Here you can basically see the model ensemble, the model forecast to the right, and then the spread that you see there in model is basically showing good, strong La Nina conditions. So cross your fingers. And how La Nina events translate to snow is a good question. This is the long-term average, the black line at the Three Creeks SnowTell over the past 40 years. And on top of that, what I did is I took all of the past moderate and strong La Nina years and plotted those as well. And it's pretty compelling. You know, all of the curves are basically at or above average when there have been moderate and strong La Nina conditions. The one sort of blue curve there that fizzles out early, that was last year, right? Good season, but kind of just the bottom fell out in April when it got really dry and warm. Let's get away from the ocean though for a moment, and let's get back to talking about seasonal snow. There's really three ways that we sort of get information about, oh, I'm sorry. This is what I was looking at in terms of the various SnowTell curves that you see there. So the black line is what we're looking at in terms of the long-term average. And then all of the individual curves are the moderate and strong La Nina years. All right, so that's what I was intending to show. So let's actually talk now about ways that we get snow information, right? We can directly measure the snow, we can remotely sense various properties of the snow, or we can use models to sort of fill the gaps and get estimates, our best estimates about snow conditions. And the types of things that we're usually interested in are water equivalent, snow depth, or vertical structure of the snowpack. So water equivalent or weight measurements, these are most commonly done in situ. Remote sensing of water equivalent is kind of a tricky thing. NASA's still working on it, and they kind of hope to have a global satellite in about 5 or 6 years, which is going to measure SWE globally. But for now, SWE is typically measured in situ using coring devices like a federal sample to extract and weigh a core of snow, or it's also done with automated snow pillows, right? And so basically what these are is just a fluid-filled bladder, which measures pressure and essentially is just weighing the weight of the snowpack that lies above it. And the curves that we get, the SWE curves, that's basically the source of data that leads to what I just showed you a moment ago. Now, depth measurements, much easier, right? You don't need some fancy instrumentation electronics to telemeter this information from a snow pillow. You just need a meter stick, you need an avalanche probe, go out, sort of sample around in a few spots, make sure you're not hitting rocks or logs, average that number and call it good. I do want to mention that there are numerous citizen science programs out there that collect depth measurements. So CocoRa's is one that's been around for a long time, and it has a really huge network of what are called basically backyard observers. School programs do this. People who measure snow in their backyard report it to CocoRa's, and it gets fed up to the internet. The Community Snow Observations Project is another one, and this basically prioritizes getting snow information from high mountain environments, from backcountry recreationists and backcountry snow professionals. Now, remote sensing is amazing, right? These measurements can be made from fixed platforms like instrument towers. They can be made from mobile platforms like like planes or drones or satellites. And it's really straightforward. The distance between the measurement device and the bare ground is known. It's either measured directly or it's obtained through GPS measurements. And then the distance between the measurement platform and the snow surface is measured, right, by basically timing how long it takes a signal to travel from the instrument down to the snow surface and back up to the instrument. Simple subtraction then gives you the depth of the snow. Now, for a fixed platform, sort of repeated measurements will give you a time series of snow depth at a given location. And if it's a mobile platform, repeated measurements end up giving you a sort of a mosaic together high resolution spatial map of snow information. And programs like NASA's Airborne Snow Observatory or SNOX, which is the snow experiment, they use airplanes to repeatedly map selected domains. And I also want to mention that the recently launched ICESat-2 satellite, very cool mission, provides global measurements of elevation. Now, ICESat really kind of prioritizes polar applications, but even at mid-latitudes, they have pretty decent coverage. I mean, so you can get like snow depths with lasers from space, all right? It's about as cool as it gets. Something else is that there are a wide variety of satellite assets out there that provide snow cover in a variety of ways, either from visual images or using various spectral bands that give you information where you can infer snow cover. So on the left, this is a typical image that you would get from the Sentinel-2 satellite. And on the right, this is a reconstruction of snow cover that you get from the MODIS sensor, which is carried by the Aqua and the Terra satellites. So snow models basically step in and they kind of fill the gaps between measurements. And there's a lot to like about this approach because computers are fast, they work overtime, they don't get cold toes out in the field. So it's a really good tool to have in our toolbox. What you're looking at here is an image from the Snow Data Assimilation System, or SNODAS. And this is sort of showing you the continental United States coverage of SWE on a particular day. And SNODAS products are great. They're daily products. They're easy to get and explore. They're relatively coarse, so they're at a 1 kilometer spatial resolution. Now, at a much higher spatial resolution, the CSO project, we've just started recently doing operational modeling. And what this means is that we're serving up high resolution, like 20 to 50 meter grids of snow information on a daily basis at mountainsnow.org. So at this site, you can kind of explore and you can download different layers of snow information. And the general idea, actually, let me come to it here. Nope, back. There we go. The general idea is that this gives people sort of a real-time tool where they can kind of go out and with at very high spatial resolution, investigate what's going on, okay, with their local snowpack. And if you're already pulling out your phones to check this out, don't pay attention to the talk. But then also I want to point out that mountainsnow.org works much better on a tablet or a desktop. It's a lot of information to cram onto a phone screen. So it's something good to check out later. Okay, so that's kind of the portfolio of information out there to consider. If we're interested in looking at changes in snowpack, the most important question to ask is essentially over what time scale. So that's something important to think about. So on the one hand, we have big changes from year to year. You know, if we have like last year was like a year of bottomless powder, that tells you nothing about what's going to happen this year. And so you can have incredibly big changes from year over year. At longer time scales, we have underlying oscillations like ENSO, and these can lead to sort of 5 to 10 year variations in snowpack. And then at even longer time scales, okay, say a few decades, we can have changes in snow variables of interest. And this need for really long-term data sets really drives the choice that we make in terms of how we analyze changes in snow. There we go. So in the Western US, we're actually really well equipped to do this, which is fantastic. The Natural Resources Conservation Service, or the NRCS, maintains a very large network, of course, of snow telemetry stations. And these are continuously monitoring snow depth, weather variables, snow water equivalent, and other things. SnowTell sites, they have varying periods of record, but a lot of them came online sort of in the late 70s or early 80s. That gives us about a 40-year data set to look at in most cases. There's also a very large snow course network, which is also maintained by the NRCS. And a snow course is a location where snow depth and snow water equivalent measurements are made manually, all right, using a federal sampler. And this is typically done maybe once a month. And it's even done over in my neck of the woods, which is great. So if you've not skied Mary's Peak, really, really nice laps. You have to catch it at the right time though. Getting your car up there can be really hard and so on, but it's a great place to ski in the Coast Range. So there are, in addition to snow courses and SnowTell, there are even more sources of snow information. All right, a lot of states have their own snow survey programs. A lot of state departments of transportation collect snow depth information. Of course, the regional avalanche centers do as well. So if you like data, being in snow is a really great place to be. Okay, so with all that, what really matters, okay, in terms of quantifying snow? So this is a very simplified look at a SWE curve, right? We have an accumulation phase through the winter and then a much steeper ablation phase when the snow all starts disappearing. Now, the vast majority of studies that have been done looking at snow conditions basically look at that peak value, all right? The reason for this is that, remember, snow courses, which are very, very many in number, only collect data monthly. So you only have 4 or 5 measurements to look at. April is typically the time of peak SWE, and so April 1st is kind of the standard date that people look at when they assess snow changes. But there's a lot of reasons why that may not be the best choice. So if there's something that happens climatically to essentially shift our SWE curve either back a couple of weeks or forward a couple of weeks, then that April 1st measurement is going to massively undersample, okay, or underrepresent how much snow is actually on the ground. So a different measure of how snow is distributed over the season is a good idea. Okay. So we can look at the number of snow-covered days as an additional metric. Now, remember, snow courses, since they only have monthly measurements, you can't really use that to calculate snow-covered days. You have to really restrict yourself to using the snow telemetry stations. So there are fewer studies out there that have looked at this, but there are some. Now, if the shape of the SWE curve never changed, if that triangle kind of preserved its shape, then the height, that April 1st SWE and the number of snow-covered days, that would tell you everything that you would need to know about your snowpack and how it's changing. But in a lot of areas, snowpack is becoming way more intermittent, right? We have a lot of warming events. We might have a lot of rain on snow events. So we get a curve that looks like this orange line where it's sort of taking stutter steps as we kind of go through this accumulation phase before everything disappears during the ablation phase. So a couple of years ago, Musselman et al. Introduced this idea of a melt fraction. And the whole idea behind this is to kind of quantify how much melt is occurring in the snowpack before the April 1st date. Now, if you look at that purple line there, which just ramps up and ramps down, the melt fraction of that would be 0 because all of the melt is occurring after April 1st. And if you look at that sort of cartoon sketch of that orange line I drew, that might have a melt fraction of about 50%, right? We keep losing snow, we get some back, we lose more, and then we lose it all after April 1st. So one more thing I want to throw at you, though, is that even this melt fraction may not be the best measure, okay, of the true value of snow. And the true value of snow has a lot of different things. It has recreation value, but it also has flood reduction value. It stores the snow and hangs on to it before it releases it into streams. It provides ecosystem services. It does lots of different things. So in this above example, that purple and orange lines that I talked about on the previous slide, they have very different melt fraction values, but if you look at them, they both more or less look like we have the same amount of snow on the ground during the season. One's just a bit more wiggly than the other. So we've kind of proposed this different idea that people start looking at the area under the curve of the snowpack, or what we refer to as the snow storage. So that last line with that green hatch marks, you can imagine kind of adding that up or integrating over time, how much snow is on the ground, and using that as perhaps the best measure, okay, of your snow resource. Okay, so let's go ahead and look at this. Let's start by looking at some of the major inputs to snow, right? People are familiar with these kinds of maps, which basically show that we have warm, wet conditions, of course, close to the coast, maritime snowpack, and then drier, cooler conditions inland. Now, these particular plots are for a 1980 to 2010 climatology, and what I'm showing you are winter values only. Okay, so on the right, this is basically your average winter temperature over December, January, February. And then on the left, this is the accumulated winter precipitation over those 3 months. And it's the combination of this wet and cold that gives us, right, the actual precipitation that we get as snow. So what you're looking at here is not total precipitation. This is the precipitation that falls as snow, yet it's expressed as water equivalent, which is why the value looks fairly low. And we can see that we have this narrow spine in the Oregon Cascades. You got the Willows out there, and then up in Washington, we have this much broader footprint of snow. If you're curious, in Oregon, spatially averaged over the state, we get about 700 millimeters or so of precipitation in a given year, and about 15% of that falls as snow. And again, that's averaged over the state and has a lot of variability, of course. So let's look at historic changes. This is from the 2014 National Climate Assessment. And what you're looking at in terms of the spatial map, these are temperatures from 1991 to 2012. Okay, so a fairly recent period compared to a 1900 to 1960 baseline average, right? So this is the way that the National Climate Assessment quantifies this. Basically, by being red, it's simply indicating no surprise that recent conditions have been much warmer than that baseline period. And in the Pacific Northwest, we're presently about 1.5 degrees above that baseline period. Precipitation's a little bit trickier and a little bit more nuanced. This figure again is showing you this departure or this anomaly from 1991 to 2012 compared to the 1900 to 1960 baseline period. And it's green, so it's wetter than normal. Part of that is coming from big droughts in the 30s and 50s, all right? But nevertheless, we think things are running a bit wetter than normal. Okay, so how does all this information show up in terms of changes in the snowpack? So there's a lot going on, and let me kind of walk you through this figure. So on the left, basically I've plotted up 700 snow course locations, okay, in the Western US, and they're colored by elevation, right? So the cool colors you see in the Pacific Northwest, our SnowTell sites tend to be fairly low. In the Rocky Mountain states, High Sierra, the SnowTell stations are a lot higher, all right? So that's what we're looking at in terms of those colors. So over a 50-year period, what I did is I calculated the percent change in the April 1st snowpack. So in the figure on the right, if you see gray dots, those are SnowTell stations where there may have been a change, but it wasn't statistically significant. All right. The other symbols are colored according to the amount of change over that 50-year period. Okay, so one location out of all of those shows a positive change. There's a blue dot somewhere over there. Looks like, yeah, it's in southern Wyoming there, that's right. And then there are 224 of those stations that show negative changes, okay? And the mean percentage change for the stations showing those negative changes is minus 40% over that 50-year period. Okay, that was the snow courses. We can also look at the SnowTell stations, which have daily data, which allow us to do different things. So remember, these have shorter periods of record than the snow courses. And what that means, remember I said determining changes depends upon the period of time that you're looking at. So with a shorter time period, it's going to be less likely perhaps that we will find statistically significant changes. So what I've done here is I've kept 500 of the SnowTell sites that have had a 40-year period of record. And on the left, what I'm showing you is the percent change over that time period in April 1st SWE, right? And about 3 stations are showing increases, about 50 stations are showing decreases. On the right, what I am showing you is I am showing you the calculated changes in this snow storage parameter, which is this integrated area under the curve of the SWE curve. And there are some interesting differences, and that's kind of worth talking about. Like in Utah, for example, there's a big cluster of stations that indicate a lot of reduction in April 1st SWE, but there's far less reduction in the snow storage. And this can be due to the fact that snow might be on the ground for a longer time. So that SWE peak is down, but the curve is broader. All right, so we're not losing as much snow, let's say. Okay. In Oregon, we see fairly minimal loss of April 1 SWE at the SnowTell sites, but there's a greater loss of snow storage. And this could be due to the fact that there's snow on the ground for less time. So that peak isn't changing, but on the shoulder seasons, things are creeping in a little bit and giving us less snow being stored overall. Bottom line, though, sort of take-home message is there's not a lot of blue markers in these figures, which is a little bit regrettable. We can also analyze historic trends in snow storage by using gridded reanalysis products. So everything I've been showing you is point data. We've got these SnowTell stations. Here, what I'm doing is I'm using a 4-kilometer gridded product of snow that comes from the University of Arizona. And again, I'm showing you these historic changes in snow storage. And I'm doing it here for different months. All right. So on the left-hand side, we're looking at kind of computed changes in snow storage in the middle of winter, looking at February. All right. We see reductions in a lot of the West Coast. We do see some blue kind of over in the Rocky Mountain states and places like up in North Dakota and so forth. On the right, I'm showing you changes in snow storage in November. So this is kind of one of these more sort of shoulder months, if you will. All right. And there's far more loss. And that's consistent with the idea of the middle of winter staying reasonable, but starting to kind of erode away, perhaps at some of those shoulder months. Okay, so that's all in the rearview mirror. That's historic stuff. What about the future? Well, we don't have data for the future. This is where climate models come in, of course. Snowpack models use weather data as input, and so we have to kind of figure out where to go from there. We can model things for different conditions, of course. People have heard of probably these different RCP scenarios, kind of optimistic, pessimistic, and so forth. We can also model things for different time periods, and then we can run a whole suite of climate models and kind of average the results. So as an example of snow drivers, these are long-range pessimistic estimates, okay, of temperature and precipitation changes for end of century, right? Oh, sorry, again, I lost my track of where I am. We've got kind of broad increases in temperature on the left. We also see fairly significant increases of precipitation on the right, right? This is kind of a good news, bad news situation. More precip coming. Is it going to fall more as rain or as snow? That's the question. So I used to give this talk with a lot of sort of results that I've generated myself, but I wanted to switch things up here and just show you hot off of the presses. This is a big review that came out just last month in Nature Reviews by a large collection of authors. And what they did is basically a summary of, okay, a whole bunch of different results. And what you're looking at here is basically showing you on the left, these are kind of whisker plots. So the black line is kind of the average of a whole bunch of studies. The thin black lines are showing you kind of the bound of estimates of a whole bunch of studies. There's about 20 studies that fed into this review. And you can sort of see as you go through the different time periods, what they're showing you is this reduction in kind of peak SWE that is expected. Okay, so I'm going to go ahead and wrap this up and basically say that I don't have all of the answers, all right? But I want to leave you with the following, okay? If you walk out of here feeling like you maybe are aware of different sources of snow information that you can go look at, that's my main goal here. That's what I'm here to kind of educate people about. We are really fortunate in the United States that we have all of this information publicly available to us. It's a great thing. A lot of other countries don't have that. And as a snow scientist and as a snow recreationist, I'm thrilled about that. So, you know, as you basically educate yourselves about the past, present, and future of snow, I hope that you enjoy doing that. And I just want to say thanks for the time. And as you plan for this season, stay safe, stay informed. And the answer is yes to all three, by the way. I promise I will care. All right. So thanks again.